I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life,
The podcast that helps you understand the chemistry of your everyday life. And if it's one of your first times listening to our podcast, Melissa really, truly is a chemist.
That's right, baby, a doctor.
Yep. She has her PhD and she's a real chemist. She's been immersed in the world of chemistry for a very long time. And I truly am not a chemist in any way. And so we're being very honest. In every single episode, Melissa teaches me something about chemistry in everyday life.
Mm-hmm.
And I'm learning it just like you guys for the very first time.
Yep.
Live. And then I have to repeat it back live also.
Yes. He does not get a practice run.
That's very true.
So I did tell Jam that we were doing volcanoes.
And usually I have, like, if anything, like a 5-minute heads up.
Right,
like,
right.
Never like a week or a day even.
Yes.
But like I'm typing up the beginning, opening the project kind of stuff, and I have to label it something, and then that's when I find out what it is.
He said, "What file name should I give this?" And I said, "Volcanoes." And his face lit up, and he said, "I have a story. Well, not like I've been with volcanoes, but a story to tell you." And I have been waiting to hear it. So tell me what your story is, Jam.
Okay, yeah. So I have a childhood like fascination with volcanoes, and this is one of the stories that my mom likes to tell sometimes. If she, you know how moms gather, I mean, any parent or guardian will kind of gather stories that they might pull out frequently, especially when they want to sort of brag on their kids or whatever.
Or how like cute and funny they are. It's like the few they rotate through.
Yeah, exactly. When you were a kid, you used to, that kind of stuff.
Yeah.
So one of the ones that I remember very clearly, this obsession with volcanoes starting, and my mom also found it very interesting and liked to brag about it to other people. But I learned about some volcanoes probably, for the first time in detail, maybe like second or third grade. I can't remember when it's normal. And then I got so interested that this is back in the days of renting, movies from a rental store like Blockbuster or whatever.
You went there with your mom and your best friend after school or whatever.
Exactly. It was a highlight, or doing it on Friday and renting something for the weekend.
And we got to drink soda on Friday.
Nice. Yeah, we did too. On weekends, we could drink soda. And it was all kind of combination. So after I got into this, found out about volcanoes, got super interested in them, we went to Blockbuster, and my sights were set on, there's so many other cool videos to rent or whatever, movies to rent. I was so excited that I found a National Geographic movie video, whatever you call it, about volcanoes. And
like a documentary.
Exactly.
That's classic Jam behavior.
It really is. It's like before I got into film and documentary and stuff like that, and studied that and got my degree in it. But so we rented that, and I was glued to the TV watching this thing. None of my brothers wanted to watch it with me. My parents didn't really want to either. It was just for me. And I watched from beginning to end, all in one sitting, this documentary about volcanoes. And I remember there being, it crossed from, talk about different volcanoes. It wasn't just about one, but they had a pretty in-depth story about Vesuvius erupting and Pompeii, and that, really famous story and all that stuff. I remember it pretty well, surprisingly. And who knows how many other movies I watched as a kid, I don't remember. But I love volcanoes. They're certainly super scary.
Right.
But from such an early age, something about them is so captivating to me. And so I'm super interested to learn about them some more.
Well, guess what? I also have a story.
Okay.
So when I was little, I don't really remember the order of these things. My mom doesn't have a story, but I also loved volcanoes. I especially loved watching the lava or the magma turn into rock.
Yeah.
And the noises it makes, like as it's kind of like coming down and solidifying.
Yes.
And the texture of it. And I just wanted to touch it so bad.
Yes.
Obviously, I knew that it would not be good to do it, but it was just so beautiful. I was just entranced by it.
Totally. Yeah.
And I'm pretty sure I read this book called Escape from Pompeii. Did you read that since you also loved volcanoes?
I don't know if I did.
Well, then I was thinking about it because I don't think people did escape from Pompeii. So I'm like, what is that?
Yeah.
But so I remember reading a book about Pompeii that I was shocked and horrified to find that people were just like basically frozen.
Yeah.
In what they were doing the minute they got overtaken by, I think it was ash, technically.
Right.
So, yeah, that fascinated me too. And then I found that you could be something called a volcanologist. That's the person who specializes in studying volcanoes. And I wanted to be that.
Yeah.
But guess what?
What?
I could do that right now if I wanted, because you have to have a background in chemistry.
Nice. Very cool.
So if I wanted to switch gears, I could, but I decided that it was a dangerous career. And also I hate being hot. So it's like, is that a good career for me? And I honestly, my life doesn't really work for me to travel to beautiful places all the time, financially and or otherwise.
Yeah.
So even though I gave up my dreams of studying volcanoes in favor of sitting in an air-conditioned room and chatting with you in Denton, Texas, when I could be at beautiful mountain sides, volcano sides, there are other people who didn't give up on those dreams, and they do study. They study both I think they study the development of the volcano and trying to find tools to predict the volcano and how they develop, because there's different pathways for the magma. And so it seemed like they studied those processes, the biogeochemical processes, to learn as much as we can about volcanoes so that we could be more prepared for volcanoes.
And I didn't really know. I learned during my early volcano obsession that was a profession that existed. Like that could be something you study, because it actually was, I think, a different documentary I watched. So I guess I did this more than once. But there's this couple, and they're both volcanologists together. You heard about them? Yeah.
Yes.
And in one of the documentaries I watched, it was like, you got to see a lot of the things that they did and places they went. But at the end, it was like, and sadly, this couple, both of them, lost their lives while trying to get to a volcano, and it like they got trapped or something like that.
I think we may have talked about this before, but I also think that I didn't want to be a downer, but since you brought it up, I think that profession has a very high rate of death associated with it.
Yeah, it's like, it makes sense, but it's super sad, but also cool that people are willing to risk it for the sake of a lot of good things to find out about.
I kind of put it on the level of being an astronaut. Like the willingness to explore an unknown frontier that is so powerful and dangerous.
Yeah.
And that has so many unknowns, and that puts your life consistently at risk and requires you to take so much time away from your family.
Yeah.
And for volcanologists, they have to do it at the drop of a hat sometimes.
Yeah.
And so I think that career is one that we should think is as amazing as astronauts, but we don't seem to talk about it very much.
Yeah.
But I am going to talk about it today because I think it's amazing. Yes. So some of the chemistry in volcanoes we're going to touch on today. Volcanoes are very complex. They're pretty amazing. It ties together polymers, thermal expansion, gas, solubility of gas, pressure, how molecules interact with each other, similar to what we talked about with the wind. And there's also so much more science in it. So I just kind of wanted to give you a broad overview of some chemical principles at play, but I'm sure I could do a whole series on it. And I do kind of want to reach out to someone who studies this. I did find somebody who touched on something, whose research was on something that we're going to touch on today. So hopefully that person will respond to me, and then maybe we could interview someone from volcano chemistry. Amazing. Yeah. So my quick summary of what volcanoes are is very similar to what happens when Diet Coke and Mentos do that thing.
Oh.
So we talked about that. Now there's a nucleation site in that sort of, the nucleation site is the impetus for the thing that happens, and that part is different.
Okay.
But the general idea of air escaping and bringing magma, or I guess it becomes lava, I think, when it comes outside, bringing those things out with it, that's very similar to what we saw.
Ah,
There's a contained space, there's air rushing out, and there's so much air rushing out so quickly that the liquid gets caught up in it.
got it. Okay, I've never heard it put that way. Not that I can remember anyway. Not that I yeah, that's okay. Interesting.
I hadn't heard it. I've heard people talking about, and there was a lot of quotes about, oh, it's just like when you release a soda can and you hear the gas comes out,
Yeah.
that volcanoes are off-gassing, but then they didn't talk about the explosion being like the Diet Coke and Mentos, and I was like, they're so similar.
Yeah.
I guess probably not everyone has done an in-depth chemistry episode about the phenomenon of Diet Coke and Mentos, so I kind of had that unique perspective.
Yeah.
So the impetus for the rush of air is different, but the explosion, the stuff coming out of the earth is very similar in that it's driven by air rushing out.
Okay.
So that's kind of the overview. I wanted to give you the big picture, and then we'll talk about sort of why that happens.
Okay.
And also, we'll talk about why sometimes volcanoes explode and sometimes they have more what they call peaceful eruptions. Okay. Before I get started, I found a quote that I really appreciate from the National Academies Press, and I think that's a council that will, I don't know how exactly this comes to be, but they will regularly put out books summarizing what we know in a field and putting out a call for what more needs to be done.
Okay.
So there's one of those for my field for discipline-based education research, and I quoted it in my dissertation. The National Academies Press book said that we need more of this kind of study.
Got it.
So they summarized this as, I think this one was 2017 or 2019. They summarized the current state of volcanoes and said, quote, a central challenge for developing models is that volcanic eruptions are complex, multi-phase, so phase, as an aside, phase meaning solid, liquid, gas, and multi-component systems that involve interacting processes over a wide range of length and time scales. For example, they're referring to magma as an aside. For example, during storage and ascent, so rising of the magma, the composition, temperature, and physical properties of magma and host rocks evolve. Bubbles and crystals nucleate and grow in magma, and in turn, they influence the properties of the magma and lava. So that is a good overview of why it's going to be difficult for me to give you a really very solid, oh, this is what we're talking about today, right?
Got it.
But I am going to be able to talk to you about the gas molecules and what they're doing and what the chemical composition of the lava how that can impact the explosions and why some explode crazily and some explode peacefully.
Okay.
So I'm not trying to cover the whole scope of doing volcanoes because I think only a volcano expert could truly talk about that. And even then, I think this is one of those gray areas, like we talked about a few weeks ago, where it's hard to know everything. And there's probably theories, but not a lot of this for sure is what's going on.
Right.
So I tried to hold on to things that I could easily say, as a chemist, I am highly confident that this is what's happening.
Okay.
And then I also wanted to say, I used that National Academies book, but there's also a really good article that I'm going to link to that came out from the Royal Society of Chemistry that talked about volcanoes, and we'll link to it in our references as always. But I really wanted to give the Royal Society of Chemistry a shout out because they summarized it really well in a way that focused on the chemical principles at play. So I did rely heavily on that as well.
Okay.
And also the Royal Society of Chemistry has been one of our sponsors in the past. They have some really cool chemistry podcast resources and stuff like that. So go check them out. We really appreciate them. They're essentially like the American Chemical Society, but over in the UK.
Nice.
So shout out to them. Thank you for that article. That was awesome. And it'll be linked in our show notes. Okay, so as I mentioned, what essentially happens with volcanoes is there's a big Diet Coke and Mentos situation.
Okay.
Or, so it either does the big explosion, Diet Coke and Mentos, poof, it all comes out.
Right.
Or more peaceful explosions could be sort of like if you just have a 2-liter that gets shooken up and you open it and it kind of spills out, but it's not a crazy explosion.
Right.
You can expect to see both of those different kinds of explosions from volcanoes.
Okay.
So big explosive eruptions and then more peaceful eruptions.
Okay.
And I bet you wouldn't have guessed this, but chemistry can explain some of why that happens.
Huh.
Are you shocked?
Are you sure?
I'm so sure, but I'm also so sure that there's a lot more that we don't know yet.
You mean chemistry with the beakers and the test tubes and the Erlenmeyer flasks? That has something to do with
that
volcanoes?
very same one. Yeah.
What the heck?
Absolutely.
What the hey? Just thinking like of suddenly like a 1940s like sitcom dad.
Dude, you would be a great 1940s sitcom dad. Classic.
I don't know if I could handle it. I think it'd be funny to do it to be funny, but like
if you meant it in earnest.
If you meant it in earnest and that was really how you were, I think I would, that would not have fun. But it's funny to do it now as like an anachronism.
Right.
You know, but anyway.
So the Earth, a lot of people I think know this already, but just a quick review. The Earth is not just a big ball of solid rock. There is a liquid core that's actually I think it's iron rich. And then there's 2 more solid layers on the top, solid-ish.
Right.
So there's the core, and then the mantle is one of those solid layers, and then the crust is what we live on, hang out on. It's solid-ish. There's water on top of the crust, obviously oceans, lakes, waterfalls, rivers, whatever.
Yeah.
So somewhere in the bottom of the crust and the top of the mantle, even though it's all mostly solid, there is liquid.
Okay.
And that liquid is called magma. And we know, I didn't know this until I read about it. I assumed that came from the liquid core.
Uh-huh.
But we know that magma does not come from the liquid core because the chemical composition of magma is different.
Okay, interesting.
So magma seems to be a mixture of melted rock that's very, very hot. That's why it's liquid.
Mm-hmm.
It also is under quite a bit of pressure. There are gases that are able to be dissolved in this liquid because they're under pressure. And
Right.
We're going to pause here for a chemistry lesson. We've talked about solubility a lot. And for solids and liquids, things dissolve more easily in solids when solids dissolve more easily in liquids when the liquids are hot. And people have seen that with hot tea versus cold tea usually is the best example. But you've seen the opposite with gases, whether or not you realize it. But for soda, for example, gas more easily dissolves in soda that's under high pressure and that's cold.
Right.
Which is why drinks go flat faster if they're not in the fridge, soda drinks. And why when you release the pressure, you hear the psst of air coming out. So although it doesn't have the advantage of being cold in this magma liquid, it's under so much pressure that these gases can stay dissolved in the liquefied rock.
Got it. Okay.
So the other thing that there are, and this is the person who's studying this, is the person I reached out to, is there are some crystals that form in the magma. And I saw this referenced a few times in the Volcanoes book, even in that quote I read earlier. But I don't understand how crystals can be forming out of liquid when there's so much pressure. And crystals are typically crystalline solids that have a very highly repeated structure of a very pure solid.
Yeah.
So I'm very confused about that.
Yeah.
And so I was down a rabbit hole looking into that, and I found someone who did research into the crystalline solids in volcanoes and investigating some of the patterns in the molecules forensically to try to figure out what happened in the volcano. In the same way forensic chemists recreate a crime scene.
Yeah.
This sort of forensic volcanologist was looking at these crystalline solids, I guess after eruptions, identifying these and looking for patterns in the molecular structure that gave clues about the development of the volcano.
Interesting.
Which isn't that so weird?
That is so weird.
And also so cool.
Yeah. And I'm still like, also like, one, I'm amazed by that. too. I'm also
Right.
still like, but yeah, why are there crystals in there?
Why are there random solid crystals? And maybe they're
Yeah.
not the same type of crystals that I think of. Maybe crystals mean something different in this discipline, but it didn't seem like it as I was going through. And so if that person who studies that wants to reach out, or if there's anyone who studies volcanoes that also listens to the podcast, first of all, Jam and I are going to fangirl over you so hard.
Yeah, absolutely.
So hard. But we want to listen to you, and we want you to come on and talk about your expertise and explain crystals to us and explain everything to us, because that goes beyond my understanding as a chemist. Is how can there be something that I know to be highly pure and very difficult to create and needing very specific situations and also cooler temperatures usually?
Yeah.
How can that exist in magma?
Yeah.
That's a question I really want answered, and I couldn't figure it out. I know there is an answer, but the chemistry of volcanoes is a little bit beyond me in that way, I guess, or the science of volcanoes.
Yeah.
And also I was going to say, I did take a class in college called Natural Disasters that focused on earthquakes and volcanoes. So I've even taken classes on this, and it's still so complicated that I was baffled.
Yeah. Dang.
So I would love to talk to somebody who studies volcanoes. So if y'all know volcanoes, research scientists, please reach out to me. Okay. So that's what magma is. Melted rock, gas, crystalline solids. All of those are all under all the pressure of the Earth's crust. Can you imagine how much pressure that is?
No, I mean, no way.
No way.
Yeah.
Yeah. If you just go to the bottom of the ocean, you'll be crushed. So
yeah.
High pressure environment, keeping the gas dissolved. And maybe the high pressure helps some of those liquid molecules come close enough together that they are forced to solidify. Like it's maybe fighting with the heat and the pressure, because pressure usually makes molecules go closer together and makes them solid. That could be part of it, but I still don't know how it could be crystalline. Okay.
Yeah.
So that's what magma is, but there's different types of magma. There are pretty much classified, from what I can tell, based on their content of a chemical.
Yeah.
Chemistry, silicon dioxide.
Okay.
And silicon dioxide is interesting. It is also sand.
Mm-hmm.
It's glass, and it's highly abundant in the Earth's crust. And silicon and oxygen are the top two. Oxygen's the most, silicon's the second most abundant chemicals in the Earth's crust.
Wow. Dang.
So there's different types of magma, and I'm going to try to say their names. I don't think I'm going to say them right. And then from then on, I'm just going to characterize them by high silica and low silica content. Okay, so there's basaltic magma that has a lower content, that's 45 to 55% silica by weight, silicon dioxide by weight.
Okay.
And it's high in iron, magnesium, calcium, but it's lower in potassium and sodium.
Mm-hmm.
Then there's andesitic magma, I think is how you say it. And that's medium silicon dioxide content. It's 55 to 65% by weight.
Okay.
It's intermediate in other ions or elements like iron, magnesium, calcium, sodium, potassium. There's some, but not a lot, just an intermediate number. And then there's rheolitic magma, which has the highest content of silicon dioxide. It's 65 to 75%. It's low in iron, magnesium, calcium, but high in potassium and sodium. So that's just kind of what makes up the content.
Okay.
The higher the silicon dioxide content, something amazing happens.
Okay.
Okay. Are you ready?
Yes.
There can be polymerization.
Whoa.
They start to form polymers, meaning that the higher the silicon dioxide content, the thicker the magma is, so more viscous.
Okay.
It is more silicon dioxide, more viscous, because there are more long chain molecules.
Right.
So it's sort of almost just restricting the flow and the movement of the molecules because they're starting to polymerize.
Okay. Got it.
Okay. And what that means is it is harder for gases to escape because it's such a thick liquid, just like bubbling through honey versus bubbling through water.
Right, right.
One of the articles that I read suggested doing that with kids if they were having a hard time sort of visualizing this. They said blow bubbles in water and then blow bubbles in honey and see how different it is.
Ah, okay.
So
That's cool.
The higher content is more thick, harder to flow, more like honey, and then the lower silicon dioxide content is easier to flow, a little bit more liquid like water. Okay. So when magma starts to rise, and I think there are a lot of different reasons that magma will rise, the pressure starts to lift.
Okay.
What do you think happens when the pressure starts to lift? And for those of you at home, take a minute and try to think about it.
Okay.
And just to clarify, when I say pressure starts to lift, it means as the magma rises, it's under less of the Earth's crust, so there's less bearing down on it, less atmosphere bearing down on it, less pressure bearing down on it. So pressure is being taken away. So what do you think happens to this liquid mass of silicon dioxide, metals, essentially melted rock, gas, and crystals, and maybe even some polymers? And maybe the crystals refer to the polymers. That'd be interesting. Okay, sorry, that was a off thing. But what do you think might happen if we start to take some of that pressure off?
Okay, my first thought, just thinking about the gas thing, is that because the pressure is decreasing, the pressure is what's keeping the gases dissolved in the magma.
Right.
And so the gas starts to have the ability to escape more easily from the magma. And so far, that's the only clear idea I have.
That was spot on.
Okay, nice.
Okay. So magma starts to rise. The pressure starts to lift. Things kind of also start to melt because with less pressure, they're less stuck together. So some more rocks start to melt into the magma, making the volume larger and making it rise even more. That's sort of similar to the idea of sea level rise coming from a combination of thermal expansion and the land ice melting. We're going to play this episode again. So if you don't know what I'm talking about, you can wait, and we're actually going to release it next week.
Yeah.
But it seems like there's two things happening: that magma starts to rise, pressure starts to lift. So there's this expansion that happens, making it able to spread out a little bit more. And as the pressure is lifting, also more rock is under less pressure. So then that's melting too, because it's really, really hot and it was only staying solid because there was a lot of pressure on it. So as it's rising, that melts too. So the volume is increasing both because it's got less pressure on it and because things are melting.
Right.
And not only that, but what you said also happens.
Okay.
The gas starts being under less pressure. So it starts to undissolve, come out of solution. The gas molecules start to meet each other. They start to run into each other. And bubbles start to form. And just like we saw with the Diet Coke and Mentos, if there's a lot of bubbles that are forming, and that is somewhat rapid, we are very rapidly getting all kinds of expansion in this volcano. So pressure is being lifted as the magma rises. Volume of the magma itself is expanding. And then more rock is melting because of the increased heat from the magma rising and then the decrease of pressure. So the volume is getting bigger from that. And then while all that's also going on, gas molecules start to find each other because they're not under pressure. So they're not staying dissolved in the solution anymore.
Right.
And as they find each other, they become larger and larger and larger. And we're rapidly running out of space in our 2-liter bottle of Volcano.
Right.
So there are kind of two options here.
Okay.
If you have a low silicon dioxide magma content that is more liquidy and less viscous, that gas can escape somewhat easily, relieving some of the insanity. It can escape, and it's not taking anything with it because there's not a lot of, really, it's probably intermolecular forces, the thickness of the polymers. There's not as much holding that gas down in the magma.
Okay.
There's not as many chemical forces or electron interaction type things that are keeping the air dissolved. It's able to break free of that surface and escape in a relatively peaceful way.
Okay.
Like when you just open a 2-liter bottle and it sort of, at first it just goes,
Right.
and then if you release even more pressure, it'll go and like doesn't do a big explosion, but starts to like rapidly rise up and run out the sides.
Yeah.
Low silicon dioxide acts like the soda can that's been shaken, but doesn't have Diet Coke and Mentos situation.
Okay.
You hear a light release of gas where some of the gas is able to get out, but then due to a chemical principle that as gas is leaving, more gas wants to maintain the equilibrium that's formed. And so it sort of starts to all rush out at once. And then the rising is still happening of the magma, and it'll sort of bubble over the edges, but it does so. It comes out of the earth and runs down the side of the volcano or wherever it's coming out of in a more peaceful way because there is significantly less trapped air because the air bubbles were able to overcome the intermolecular forces holding them in.
Got it. Okay.
Once that pressure was released, some of them could start to escape.
Mm-hmm.
If you have a high silicon dioxide content and it's acting like honey and you're bubbling air into this thick liquid that can't get out.
Right.
When it finally does get out, it's going to be violent.
Got it. Okay.
So some volcanoes erupt insanely, explosion, high intensity. Those have the rhyolitic magma that have the high silicon dioxide content because that thick, viscous, polymerized magma is forcing the air bubbles to stay in. The air bubbles don't want to stay in. And then when they run out of space, they'll rush out and they'll just bring all that stuff with them.
Right. It just hitches on for a ride.
Just like in Diet Coke and Mentos.
Yeah. That gas is trying to get out and the magma is going to hang on for dear life and come out with it basically.
So there's not a nucleation site like we have in the other one, but it's almost as if the pressure releasing is enough for there to be lots of little tiny nucleation sites and they meet up and just all come out.
Right. Okay.
Right. So that's why some volcanoes explode violently and some are more peaceful.
Got it.
Violent ones, they'll shoot stuff into the air, and then the other ones, it just kind of trickles out the side. I mean, as peaceful as molten rocks leaking out of the earth can be.
That sort of oozing, like steady flow or whatever kind of look that is not as intense or whatever.
And you know what's interesting? Most of the gases in magma are water vapor and carbon dioxide.
Huh.
I always imagined that it would be something really intense.
Yeah.
Like, oh, there's so much hydrogen sulfide. And they say that they can have bad smells. Volcanoes can, like a sulfury smell.
Yeah.
And there are some sulfur gases and chlorine gases and fluorine gases and stuff, but most of it is just water and carbon dioxide.
Huh. Wow.
And my natural disasters textbook said that silicon dioxide content and water content are the two biggest determining factors in whether or not a volcano will erupt explosively or peacefully.
Wow.
Which those are two normal things. Like silicon dioxide and water are at the beach. That's sand and water,
Yeah.
But when you put them in this new environment, they are the top two determining factors of how intense an explosion is going to be.
Yeah. Dang.
When I read that, I said out loud, whoa.
Yeah.
It's just water? Water's the gas that does the thing? That just blew my mind.
Dang, wow.
So that's it. That is why some volcanoes explode and some volcanoes don't.
Okay, interesting. Dang. That's kind of tough.
That is kind of tough. Again, I stole your thunder by doing my own analogy, but I did my analogy to a previous episode. So
Yeah. Yeah, and it really was so helpful to understand it because it, in other ways, doesn't make like real logical sense based on just kind of how most of us probably think about volcanoes and magma, and even how most of us think about like gases even being dissolved in liquids, which is already something that most of us don't understand or don't think about.
Right.
Even though we drink
soda,
carbonated drinks all the time,
Yeah.
you know? So, okay. So I think really the using carbonated drinks, using Mentos and Diet Coke or whatever, all that stuff is, to me, the most helpful thing I can think of because it already helped me understand it.
Right.
And I don't really feel like there's something that's really missing from that I need, if that makes sense. So just like any carbonated drink,
Mm-hmm.
sitting down there way in the earth, in the mantle, there already is, before there's ever a volcano, there already is just this magma, super hot liquid rock,
Mm-hmm.
which
Is not from the core.
is not from the core. And there's different kinds of it,
Mm-hmm.
but it's going to have some of the same things between all the different kinds.
Right.
And there is already gas dissolved into it.
Mm-hmm.
It's already
more gas in some than others too.
more gas than some than others. And it's under this intense pressure,
Right.
which is keeping the gas there dissolved into the magma.
Right.
And then separate from the gas, the makeup of the magma varies a lot
Mm-hmm.
based on what is in it, which can make the magma a lot thicker,
Right.
a lot more viscous, or thinner, less
Mhm.
viscous, and lots of different things make that up. But it has a pretty significant effect on the eruption
Right.
and the gas being held in it or not. And so when this magma has an opportunity to rise up a little bit and move into an area of less pressure,
Right.
as it gets closer to the crust, there's less pressure on it.
Mm-hmm.
The gas starts to have the ability to come out of solution.
Mm-hmm.
These gas atoms and molecules can start finding each other and creating larger and larger bubbles
Mm-hmm.
of gas together, sort of fighting being held captive in the magma.
And I don't know if I did a good job of explaining this, and we've talked about this a lot before, but they're really mostly held captive because there's the pressure, but also there's intermolecular forces that they can't overcome. They don't have enough energy or ability to move to overcome the intermolecular forces to meet each other and find bubbles.
Right. And so as they're able to do that, the way that it actually looks in the eruption can vary, but in all those cases, it starts to be able to create larger and larger bubbles, which can help it rise to the surface.
Mm-hmm.
But the way that it brings the magma with it can change. So in the thinner, less viscous magma, it will still bring it to the surface with it, but it might kind of just ooze out in this chill, more peaceful way.
Chill as a volcano can be.
Right.
Right.
Still like, burning lots of stuff and super dangerous for humans and whatever else and animals
Yep.
and plant life. But it is oozing out. And then in the magma that is much more viscous, has the polymers, has just overall much more thick, the gas will have a hard time kind of escaping in a peaceful way. And so as it's bringing it to the surface, as it's moving into this lower pressure area, as it gets closer and closer to the crust, it will bring the magma with it.
Mm-hmm.
And the magma just hangs on for dear life.
Yep.
And when it reaches the surface, it blasts out in this pretty violent way. And that's the analogy you gave is perfect. A soda kind of just oozing out because it was It was under some pressure, but there's no Mentos involved, nothing else involved, just being released and kind of running over the side of the cup or running out of the bottle or the can or whatever is the first situation. The thinner magma, and then the thicker polymerized magma that's much more viscous is the second situation, is the Mentos, very violent geyser of magma shooting out from the earth. And that's all I can remember.
Okay, I think that's good. While you were talking, I thought of some things, though.
Okay.
So one thought is maybe a better analogy, because where the analogy breaks down is there's not a nucleation site that forces all the gas out.
Right.
The difference is in the liquid.
Right.
So one thing I thought of is, real maple syrup is nice and runny and almost more like water.
Yeah.
And then the high fructose maple syrup that's maple syrup flavored is much thicker. So if you can imagine, or if you want to try to put a straw in a domed container, like a bottle or something like that, of each one of those and blow bubbles in it to see what I mean about how bubbles stay trapped in one and not as much on the other, and how they would explode differently. That could be a fun experiment.
Oh, interesting.
The other thing I thought about was, and this again, the liquid isn't quite a good analogy, but the gas content is a good analogy, because even with the other one, you're putting gas into it, but the gas is just coming out of the solution and it's coming out at different rates kind of to make bubbles in the different situations. But wine, when you open it, like a red wine, sometimes they'll just do like a light, like the pressure being released because it's in a wine bottle.
Right.
But if you open champagne, it's like, and it sort of does the there's a pop, it's like a very distinct noise.
Yeah.
And that's because there's a lot of dissolved gas in champagne when it's under that pressure. And when the pressure releases, you can get that pop.
Right.
And that's, I think, a good example of there's a lot of gas in this one, so it can kind of explode violently. The other one has almost no gas in it. Now, the reason there's different amounts of gas in it is different.
Yeah.
But
yeah.
that can kind of also give you an idea of why one might pop and one might not.
Yeah. Yeah.
It's just hard to get a perfect analogy because it's very rare where you'll see something where the pressure is released, and so then the bubbles that were dissolved in it start to come out, but you have that exact same thing happening in two different liquids, because the only liquid that we consistently carbonate is like water with sugar, basically.
Right.
So, but we did talk about some of those dynamics about how Diet Coke is the best and reasons why Diet Coke was the best for that explosion.
Yeah.
So that is maybe a little bit, but it's just, there are so many phenomenon similar to volcanoes, but nothing that exactly gets at all those chemical processes. So I wanted to make sure that people didn't think there was like a thing that we dropped into a volcano that made that happen. It's really just about how the thickness of the liquid keeps the gas in there for so long that there's so much more gas in there, where the other one's sort of lightly letting it go until the more gentle explosion.
Yeah.
Okay, so here are some fun facts.
Okay.
1, have you ever heard of like volcano rock with those lots of air bubbles in it?
I've seen it. Yes.
I believe one of my sources said, although I couldn't confirm it anywhere else, that comes from this magma that has all of these air bubbles in it coming out and then super cooling. And so you can see, if that's true, you can see the air bubbles in the magma.
That is incredible. That I've never thought about that, but we actually had some volcanic rock, I can't remember the name of it, in our flower bed in one of the houses I grew up in. Yeah. And I remember it being really different texture, different look, had the air bubbles, all that stuff in it, from other rocks. Right. And I was told it was volcanic, but I didn't understand that at the time.
Well, now you do.
That makes total sense. That's super cool.
There's also different types of volcanic rock. Like some is shiny and glassy because it's got a different air content, and it's glassy because there's silicon dioxide in there. So the silicon dioxide is able to essentially turn into something very close to gas in those conditions. So there's different types of volcanic rock. But I thought that was interesting because I've seen those ones with the air bubbles in it. And I was like, is that real? Is that really what that is?
Yeah. Wow. That is interesting.
That's very, very cool. And then the other thing is there are, a lot of people don't know this, but hydrogen chloride and hydrogen fluoride, or you've probably heard it called as hydrofluoric acid or hydrochloric acid.
Uh-huh.
Those acids are actually gases at room temperature, and they're just often dissolved into water for us to be able to transport them to get a high proton content, basically. And one article said that, this is a quote, acidic hydrogen chloride and hydrogen fluoride gases have been known to take the surface off researchers' glasses when they're there studying. And it is, when you open a bottle of one of those acids, you can see like a cloud come out, sort of reacting with the moisture in the air. Uh-huh. And if your face is right over it, which it shouldn't be, that's a bad safety practice.
Yeah.
It will sting your nose and you'll get like maybe even like a light chemical burn, but you'll feel that acid in your nose if you breathe it in. And it's like, and then you're like, that was stupid. Why did I do that? And we were working with it with a really small amount. So even that small amount would be like, ugh.
Yeah.
When you first opened it, the buildup that had like escaped out of the solution would go into the air. But imagining being in an environment where there's so much that it takes the surface off your glasses.
Yeah.
And then also there's toxic mercury and carbon monoxide that seep out. So there's a lot of dangers associated with volcanoes that aren't just getting trapped in a volcano.
Right.
So I thought that was interesting.
That's crazy.
I didn't know that happened, but it does make sense that it does.
Dang, yeah.
Well, we both shared little stories about our lives at the beginning of today's episode. So perhaps we can just wrap it up there so that it's not too long of an episode.
That sounds great. Yeah, this was quite a bit. This topic was quite an undertaking to sort through. So it makes sense. It took a long time.
Definitely.
To get through it, but yeah.
But so fun, so worth it. Our shared childhood obsession that we didn't know that we both had. So that's kind of cute.
Yeah, that's cool.
Well, I think that shows that you've always loved science, and that's why you're the perfect co-host for this podcast. So thanks for listening to me teach you science all the time.
Anytime, especially on this topic, but anytime.
And then also thanks to all the listeners who let us do this and who listen and make it feel like it's worth it. And that we're making an impact by sharing chemistry with so many people. And
if you've got ideas or questions about things in the world that you want to know about that you think are chemistry, like volcanoes, for instance, super awesome. It's actually chemistry, sort of. So that's way cool. And
more than sort of.
I mean, it is, but like, it's also its own study, which is what I mean too. It's like, there's so much overlap, but please reach out to us on Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, FOR, Your Life, to share your thoughts and ideas with us. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to ko-fi.com/chem4yourlife or tap the link in our show notes to donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing on your favorite podcast app or rating and writing a review on Apple Podcasts. That also helps us share chemistry with even more people. This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode could be found in our show notes and on our website. Jam Robinson is our producer, and we'd like to give a special thanks to V. Garza and S. Navarro, who reviewed this episode.